1. Document databases. Definition: store data as documents, which are self-contained sets of information about a specific subject. Example: an invoice, which includes details about customers, suppliers, dates, articles, and prices. Digital document: a file that represents a closed unit of information. 2. Structure. Organization. Documents are structured with recognizable subunits, often in a tree-like manner. Format. JSON, JavaScript object notation, is commonly used for representing complex objects in web development. 3. MongoDB Query Language, MQL. Purpose: an object-oriented language for interacting with document databases used to create, read, update, delete, and transform data. Database model consists of collections of documents. Documents can have flexible fields and structures. Methods: find, filters collections. Insert one, adds data to a collection. Update one, modifies data in a collection. Delete one, deletes documents from a collection. 4. Example usage. Query: to find invoices for a specific vendor, use db. Invoices.find, vendor, company, Miller Electro. Projection: to list customers, use db. Invoices.find, vendor, company, Miller Electro, customer.company, 1_ID, 0, which returns only specified fields. 5. Comparison with SQL. MQL versus SQL. MQL, based on JSON, evolved organically and differs from SQL, which is based on mathematical principles. Here are key details not covered in the breakdown. 1. Document database characteristics. Self-contained data set. Each document includes all relevant information for a specific fact or record. Analogous to written records, documents are similar to traditional written records. 2. Data structuring. Nesting. Field values can be nested in a tree-like manner. Complex object structure, often used for organizing documents. 3. JSON format. Syntax. JSON is particularly suited for web development in JavaScript. 4. MQL specifics. Schema-free. Documents in a collection do not require a predefined schema. Flexible fields. New fields and objects can be added at any time. 5. MQL query language. JavaScript-based, originally developed for server-side web programming. Unique identification key. Each document in a collection has a unique key. 6. Projection in MQL. Inclusion and exclusion. Fields can be included or excluded from the results. 7. MQL evolution. Organic development. MQL's concepts evolved from JSON and differ from SQL's mathematically based theories. The term document in document databases is a bit different from how we typically use the word for essays or reports. Here's a clearer breakdown. 1. Definition of document in databases. Digital record. In document databases, a document is a digital record that contains structured data about a particular entity or fact. It is similar to a self-contained data set rather than a traditional written essay or report. 2. Why they're called documents. Analogy. The term document is used because, like a physical document, it encapsulates all the information related to a specific subject or record in one place. The document format is used to organize and store data in a way that resembles a traditional written document, but is digital and structured. 3. Contents of documents. Structured data. Documents in this context can include various fields and values organized in a format like JSON. For example, an invoice document might include fields for customer details, items purchased, and prices, all organized in a hierarchical structure. Self-contained. Each document holds all necessary information about a particular record or entity, making it easy to retrieve and manipulate in a database. In summary, while the term document might evoke images of essays or reports, In document databases, it refers to a structured digital record that captures detailed information in a format suitable for storage and retrieval in a database. 1. Data as a vital resource. Companies increasingly view data as crucial, integrating both public, open, data and their own data. The growing volume of global data and continuous information services emphasize the importance of web-based data pools. 2. Impact on IT. The need for current, real-world information is shaping IT fields. Many organizations now have dedicated data management roles focusing on strategic and operational aspects of data. 3. Cost and value of data management. Developing and managing data systems can be expensive and hard to measure in terms of return. However, recognizing the long-term value of data justifies these investments. 4. Subfields of data management. Data utilization focuses on using data profitably through analytics and supporting departments like marketing and sales. Data architecture involves designing and structuring data systems, including components, interfaces, and relationships. Data administration ensures unified data coverage, security, and proper access permissions. Data technology deals with database installation, maintenance, technology management, and optimization for performance. 5. Data management plan. A document outlining strategies for data use, architecture, technology, and administration, typically prepared before implementing a database system. Overall, effective data management involves integrating operational, organizational, and technical aspects to optimize data use as a resource. 1. Art and engineering in database design. Artistic process. Understanding user requirements and creating a logical database design. Engineering process. Converting the design into a functional and efficient physical database. 2. Difference between data and information. Data, raw, unprocessed facts without inherent meaning. Information, processed data organized into context, which provides meaning and value. 3. Importance of accurate data. Timeliness and usefulness. Data must be accurate and accessible for effective decision-making. Data management, discipline focused on acquiring, storing, maintaining, and retrieving data efficiently. 4. Chapter overview. Introduction to basic concepts of data, information, and metadata. Comparison between file processing systems and database systems. Examples of desktop, workgroup, and enterprise databases. Framework for database design detailing multiple tiers of data modeling. 5. Data, information, and metadata. Data, unorganized facts, viewed as raw material. Information, data in context, providing meaning. Metadata, data that describes other data, defining structure, constraints, and context. 6. Metadata characteristics. Acts as a lens to interpret data and derive information. Provides precise context for data. 7. Data organization. Data element, the smallest unit of data. Record type, group of related data elements. Record instance, a specific set of values for a record type. File/dataset, a collection of records. 1. Focus of the book. Concentrates on data management, not human resources management. 2. 4 key actions in data management. Data creation, adding new data. Data retrieval, accessing existing data. Data modification/updating, changing existing data. Data deletion, removing data. 3. Supporting functions. Accessing data, essential for retrieving data. Organizing data, facilitates easier access. 4. 2 primary data access methods. Sequential access, requires passing through all preceding records to reach a specific record. Essential for applications like payroll and utility bills. Direct access, allows accessing a specific record without traversing previous records. Useful for ad hoc queries. 5. Data organization for access. Sequential organization. Records are stored in a specific order using a unique identifier, necessary for sequential access. Heap file, unordered records, unsuitable for sequential access. Random organization uses transformation routines, hashing algorithms for record location. Indexed organization uses an external index to locate records, facilitating direct access. 6. Database Management Systems, DBMS. A DBMS manages data access without users needing to understand the physical organization of data files. Works with files organized as sequential and/or direct access files to streamline data management. 1. Focus of early computer applications. 1960s and 1970s, primarily automated clerical tasks using file processing systems. File processing systems managed data in separate files, now mostly outdated except in some legacy systems. 2. Limitations of file processing systems. Lack of data integrity. Data redundancy leads to inconsistent and outdated information. Lack of standards. Difficulty in enforcing data naming, access, and protection standards, risking unauthorized access and data compromise. Lack of flexibility/maintainability. Difficult to modify systems for new requirements without extensive programming changes. 3. Fundamental problems. Lack of data integration. Data is isolated, making it complex and time-consuming to access and correlate information from multiple files. Lack of program data independence. File structure is embedded in application programs, making changes, e.g., field expansions, laborious and error-prone. 4. Objectives of database systems. Integration of data centralizes data to reduce redundancy and improve data sharing and consistency. Program data independence separates data structure from application programs to allow changes in data storage without affecting the programs. 5. Case study, time life. Early file processing issues. Multiple files led to data duplication and inconsistencies in customer promotions. Transition to database system. In the mid-1980s, Time Life replaced file processing systems with a database system, reducing data duplication and improving data integrity. 1. YNSI/Spark 3 Schema Architecture, 1970s. Proposed solution addressed database management issues with a 3-schema approach. Developed by Standards Planning and Requirements Committee, SPARC, of ANSI. 2. 3 Perspectives of Metadata. Conceptual schema. Role. Central schema representing the global view of the entire database. Function. Provides a unified structure for the whole database, achieving program data independence by isolating applications from physical storage changes. External schema. Role. Includes multiple user views or subschemas, each tailored to different users or user groups. Function. Defines portions of the database relevant to specific users. Internal schema. Role. Describes the physical layout of data on storage devices and the mechanisms for data access, e.g., indexes, hashed addresses. Function. Focuses on the efficiency of data storage and access and is technology dependent. 3. Functionality. Schema definition. In database terminology, schema refers to the description of metadata. Technology independence. Conceptual and external schemas are independent of technology, while the internal schema is technology dependent. User views. Generated dynamically based on logical references to the conceptual schema, unaffected by physical storage or access mechanisms. 1. Data independence. Definition. The ability to change the schema at one level without affecting schemas at higher levels. Purpose. Achieved through the 3-schema architecture. 2. 3-schema architecture. Conceptual schema represents the global structure of the database and is unaffected by changes in the internal schema. Internal schema details the physical storage and access methods, and changes here do not impact the conceptual or external schemas. External schema user views or subschemas that are completely shielded from changes in the internal schema. 3. Types of data independence. Physical data independence. Changes in internal schema, e.g., indexing methods, do not require changes to the conceptual or external schemas. Logical data independence. Changes in the conceptual schema, e.g., data model restructuring, do not affect external schemas or user views. 4. File processing systems. Two-schema architecture comprises the internal schema and the programmer's view. Lack of data independence. Changes in the internal schema require modifications to application programs, leading to a loss of data independence. 5. Importance of three-schema architecture. Hierarchical metadata. The conceptual, external, and internal schemas represent metadata from technology-independent to technology-dependent states. Data modeling and design focuses on managing and modeling metadata to achieve data independence. 1. Definition of a system. A system is a set of interrelated components working together for a specific purpose. 2. Database system properties. Self-describing. Includes both data and metadata. Metadata is stored within the database. Data meaning. Data has implicit meaning, which becomes explicit through metadata. Data integration. Achieved by the DBMS software, not manually by programmers. Access facilitation. Uses embedded pointers and indexes for efficient data access. 3. Types of database systems. Single-user database system. Supports one user at a time, often referred to as a desktop database. Multi-user database system. Supports multiple concurrent users. Workgroup database. For a small number of users or a specific workgroup. Enterprise database. For large organizations, supporting many users across various locations. 4. Enterprise database systems. May involve multiple databases organized by function within large organizations. Not always a single centralized database. Often multiple databases serve different purposes. 5. Distributed database systems. Definition: a collection of interrelated databases dispersed over a network. Distributed Database Management System, DDBMS, manages these databases, making geographical distribution transparent to users. 6. Data warehouses. Purpose: primarily for decision support applications, optimized for information retrieval rather than transaction processing. Characteristics: subject-oriented, integrated, non-volatile, and time-variant. Applications: supports business intelligence, data mining, decision analytics, and customer relationship management, CRM. 1. Database system components. DBMS, Database Management System, a software system that facilitates defining, constructing, and manipulating databases. Database, the actual data storage system. Data dictionary, stores metadata about data items, their relationships, and usage. Data repository, contains metadata about data models and application interfaces. 2. DBMS major components. Query languages, for database queries. Report generation tools, for creating reports. Security, integrity, backup, and recovery facilities. Data manipulation language, DML, for data retrieval, insertion, deletion, and modification. Data definition language, DDL, for defining database structure.